knowledge from string of material class by looking at the plate here, and it's subjected to a simple loading condition at the 4 boundaries. And then I just guess straight field of this particular form with the unknown constants C1, C2, and C3. And then I check all the requirements for the stress to be the solution of the problem. And finally, I come up with the constant. Okay, I get the constants C1, C2, C3, and verify all the conditions needed. Okay, and then I confirm that the gas stress field with the value constant C1, C2, C3, and confirm that the stress is the solution of the problem, right? I check all the condition. I check what? I check equilibrium equation. I check Beltrami-Mitchell equations. The two governing equations have to be satisfied at every point inside the body. And then I check all boundary condition on 6 surfaces. Okay, and by satisfying the boundary condition on 6 surfaces, I can get C1, C2, and C3. Okay, so once I check all those conditions, sorry, I finally get C like that. I get C1, C2, C3 like this, and this is the final form of stress that satisfy all the requirements. So I confirm that this is the solution of the problem, and then I know from the uniqueness of the solution. So I can confirm that this is the only solution of the problem that I focus on here. Okay. Once I get stress field, I can get strain field, I can get displacement field. Strain field can be obtained easily by simply plugging in strain relationship here. Okay, I plug it in, I get all components of strain tensor. Okay. For the displacement field, it's a little bit more challenging to get from strain displacement relationship. Okay, because you cannot just simply plug in. You just you need to perform the integration to get U1, U2, U3. Because the equation that you have to deal with here, you have 6 equations, but you have only U1, U2, U3. You have only 3 unknown components of the displacement field. So now you have to use all of this because of strain is compatible. So even though you have more equation, you can get the displacement field. Okay, you can go back and take a look the procedure. Okay, to get the displacement. Whenever you know strain components, you can always apply the technique that I mentioned here to get the displacement field. But the thing that I would like to emphasize, strain that is given or the strain that you got from a solving equation have to satisfy the compatibility condition. For example, for this problem, we start by guessing stress field. We check Beltrami-Mitchell equation, and we found that stress satisfy Beltrami-Mitchell equation. So that confirm that strain that you got here is compatible. So you will not have any problem with the integration of all these equations, right? Because the displacement exists. Okay. The other thing that I would like to emphasize here at the end of the process to get the displacement field, because you have to perform the integration of 6 independent differential equation, first order differential equation. So you will always you will get 6 unknown constants out of that integration process. Okay, so the unknown constant that I talk about here somehow related to rigid body motions. Okay, The constants that we got from the integration cannot be obtained if you don't have the boundary condition associated with the displacement, or if the surface SU is empty. You cannot get all constant AI and BI, okay? But for some cases, you may restrain the body against the rigid body movement in some directions. Some of the constant here can be determined uniquely, okay? Or if you restrain the body against the rigid body motion completely, all the constant here can be determined, okay? For this specific problem, if you go back and look at the problem that we focused on here, we see that at every point on the boundary, we know only the traction. There is no part of the boundary that we prescribe displacement field. So now for this case, we can say that the constant AI and BI, 6 of them here, cannot be determined. Okay, they can be arbitrary. So I can conclude that the displacement field that we got here is not unique, because this part, the rigid body motion part, is still unknown, right? It can be anything. Okay. Do you have any question about anything here related to the technique, the guessing technique? We use the option that we guess the straight field. You have to do this. You have to do in this way for one part of the problem that I asked you to do in assignment number 3, right? So you have to guess straight field and follow the procedure that I show you in this lecture. Okay. Do you have any concern, any part that you still don't understand? Is there any questions?
I have a question. When we assume straight field, and I mean I have no experiment when choosing straight field C1, C2, C3, and I choose C1, C2, C3 to C6.
Yeah, you can choose any form of straight field. Finally, you can conclude that okay, the form that you guess there can satisfy the equation or not. For example, if you guess the full set of constants, let's say that you guess 6 of them, right? You guess the straight field in terms of 6 constant. Let's say that okay, you don't have experience, so you don't know exactly that the component for shear stress should be there or not. If that is the case, so instead of have C1, C2, C3, you have C4, C5, C6, for example. If you do in that way, finally you can conclude that C4, 5, and 6 here are 0 based on the boundary condition. Because if you want to satisfy the boundary condition like this, let's say that you don't have 0 here. Let's say that you have C4, C5, C6. Okay. So yes, based on the boundary condition, some of them you will see that okay, C4, C5, C6 have to be 0. Okay.
Yes. Okay. And one more question. Example, when we assume the straight field contain maybe it's 1, it's 2, it's 3, it's 3. Is there any case when we choose that form?
What do you mean?
I mean when I assume the straight field and in this form has contain each one, each 2, It3.
But that is depend on the problem. It's depend on the problem. It's problem dependent because the form of the stress field that you get here, it may be in different form. You may have the dependence on X. It's possible, but it depends on the problem. I cannot tell you that, okay, which problem that you should assume in this form. This is based on your background. Okay, if you don't have enough background, you may not be able to guess the form correctly at the beginning. So you have to try. You have to try several times for some problem if you don't have experience. Like I told you at the beginning that guessing technique is somewhat problem experience dependent and problem dependent too, because when you change the problem, the form here can change. And what is the final form that you should guess? We don't have the rule for the form. It have to be based on your background. Because if you look at this problem based on your common sense, you should know that, okay, stress should be constant based on the information of the problem here. But if you change the loading condition at the battery, for example, okay, you change from the uniform loading condition to, for example, to linear loading condition. So now you know that stress shouldn't be constant anymore. You know what I mean, right? So I cannot tell you exactly when we should guess the form like this, or we should get the form which is independent of X, because it's problem dependent, and also depend on several type of data. Okay, for example, the loading condition may change, the geometry of the body can change too. Okay, so this is the disadvantage of the technique here. It's simple in the sense that if you can guess the right form or the good form at the beginning, the rest of the process is simple because you don't need to solve equation. You just simply check the conditions. But the first step is very important, and it's very difficult for beginners, because if you don't have any experience, I gave you one problem and asked you to guess the solution form. It may not be easy. Okay.
Yes.
So
it mean it's depend on the complex level of complex problem.
Yeah, that's right. And I told you that, okay, the technique, the guessing technique or the inward technique that I mentioned here is good for only for very simple problem. Whenever you deal with more complicated problem, this technique may not be possible, because the form of the solution may be complicated, and you cannot guess the form correctly. You know what I mean, right? So the technique that I mentioned in this class is only for simple problem. Okay, very simple problem. Okay, for example, the geometry have to be very simple. Loading condition, material properties of those data have to be simple. Okay, so if you have to deal with more complicated problem, you have to think about the other techniques. For example, the techniques that I will cover in the class that I will offer next semester, or the technique that you will learn from the other classes, like finite element techniques. Okay, those kind of techniques will be more powerful, right? If you apply to solve some complicated problems. Okay, but in this class, I don't have enough time to show you the solution procedure that good enough to solve broader class of problems. Okay, is that clear to you? Is that clear? Do you have other questions? Okay, I think he lost the connection. Okay, I can move to the different approach. I will solve the problem again by guessing this displacement field. Okay. For this problem, again, based on the loading condition that I have here. So because of the traction that we apply here is constant. So I guess I think that okay, stress and strain here should be constant, right? So I think that okay, the displacement, if the strain is constant, because strain can be obtained by the derivative of the displacement, or you can think about that the displacement can be obtained by the integration of the strain. If strain is constant, so the displacement should be linear, right? So now I can think about guessing the solution for this problem. By guessing, I can guess the displacement field in a linear form. Okay. So to come back to the same point, how can I know that the displacement here is linear? I have to tell you that okay, I don't know exactly the form here is right or not until I check all the conditions. But based on my feeling, I think that the displacement should be linear because from the information of the problem, like loading condition, geometry, material properties. So I feel like that the displacement should be linear. So then I guess the form like this. This is a more general form for the linear function in 3D, right? Okay, this is the more general form of the linear function. And the constant that sit here, we have 12 constants, okay, to be determined. I leave all the constant here, okay, because I don't know exactly the value of all these constants. And also, I have to accept that the form that I gave here may not be correct, may not be right, okay? So if I proceed by checking all the equation that I need, and I found at the end that the displacement that I get here cannot satisfy some of the conditions. Now I can say that the gate displacement field here is wrong. I have to come back and fix the form that I guessed. I will guess, you know. Is that clear? When I guess this, you should, when you guess the form of the solution, you shouldn't expect that that is the correct form. That's the only correct form because you don't know. Okay, based on your intuition, you may think okay, the form should be like this, but you cannot confirm until you check all the conditions. There will be a chance that the form that you get here is wrong. So if that is the case, you have to come back and guess again, and then you do the thing like this, repeat it for several times until you get the solution. Okay, don't worry, fam. Okay, because I saw it. You know you have problem with the connection. Do you have more question? More question? Any question?
No. I have no more question.
Okay, that's okay. That's good. Okay, so now I check. How can I check the gas displacement field here? Once I get the form of the displacement field, you can think about checking the displacement directly based on Navier equation, right? But here I will try to show you that okay, even though I guess this displacement field alone, I can also check the solution by using you know the first procedure, the first approach that I check all fields. I can generate the two remaining fields easily. Whenever I guess the displacement field, now I can generate the strain field, right? I can use strain displacement relationship to generate strain field by simply plugging in here, right? I plug in the displacement components into this strain displacement relationship. Now I can get strain field, all component of the strain tensor, right? So this step should be straightforward, right? This is the final strain field that I got. I didn't show you in detail because the differentiation that you have to get involved here is simple, right? For example, epsilon 1, 1, you just simply take u1, comma 1, right? u1 is this one. You take the differentiation of this one with respect to x1. You're going to get b1, 1. So epsilon 1, 1 going to be b1, 1. Okay? And the rest of the components can be obtained in the same way. If you look at the components of the strain tensor that I got from the displacement field here, you can see that it doesn't involve AI, right? Because AI, A1, A2, A3 here can be considered as the rigid body translation, so it will not generate strain at all. So you shouldn't surprise that AI disappear from strain tensor. Okay. Now, when I get strain components, I can get stress as well. Okay, I can get stress easily based on this relationship. Okay, the generation of stress, we just simply plug in strain component that we got here. Okay, plug it in this relationship. Now we can get stress components. Okay, is that clear to you? I just plug it in, but in the problem that I solve here, the material constants are given in terms of E and Young and Poisson ratio, right? We know E, the Young modulus and Poisson ratio. So if we plan to use this stress-strain relationship, stress in terms of strain, in terms of the constant lambda and mu. So we have to express lambda and mu in terms of the given constant E and Poisson ratio. Okay, because if people that's not in this area, if they are not in this area, so they don't know exactly this relationship. So you have to provide this. If you try to use some relationship that are not directly connected to the given data, so you have to provide the connection there too. Okay, so here we know that E and Poisson ratio are given. So if you try to use the relationship like this, lambda and mu have to be expressed in terms of E and Poisson ratio like this. Okay, now I can get stress component like this. This is just simply plugging in, right? Because we have strain component, we have this relationship, you plug it in on the right hand side. Now you get components of stress tensor like this. Okay, so now we start by guessing the displacement field. We can generate the remaining two fields, strain and stress, by using these two relationships. Now I can say that we have all fields. Okay, we have displacement, we have strain, and we have stress. And two governing equations are already satisfied, right? Because that one is already satisfied. That one is already satisfied. Without, we don't need to check those two equations anymore because we use them to generate strain and stress. So if you think about strain, displacement and strain that you got here, we can say that these two equations are satisfied automatically. Okay, so if you go back to the first option that I mentioned there, that whenever we know, or whenever we are given all fields, if we want to confirm that the field that we have in hand is solution of the problem, we have to check all three field equations, right? Here we have this, we face with the same situation, right? Because we can say that up to this point, we know U, we know epsilon, and we know sigma. If we want to confirm that all of them here are solution, we have to check the governing equation first. All the two here are satisfied, so it still remain one set of equation that we have to verify. Which one? Can you tell me? We have three types of equations, right? The one that we haven't checked is what? Equilibrium equation, right? That's the only one that we have to check here because the two here are satisfied automatically. So the next step, I have to check equilibrium equations. I have this equation, right? And for this particular problem, Pi is 0, right? We don't have body force field for this particular problem. So that term disappears from the equation, right? How about the first one? The first term here. If you go back to stress component that you got before, I mentioned that here, that stress is constant, right? Because strain is constant, that it is independent of X. So stress is constant because strain is constant. So you can see that all the entry here are independent of X. So now derivative of stress components with respect to any coordinates will be 0, right? So that end up with the conclusion that the term here disappear too automatically. It doesn't depend on the values of the constant that we have there. Okay, so that term is disappear. So I can say that equilibrium equation is satisfied automatically for the choice that we guess there. Okay, so what I try to say here, the gas displacement field in a linear form produce strain field, produce constant strain and stress field that satisfy all equation inside, right? So we cannot get all the constant there based on the governing equation at every point inside. Now we have to depend on the boundary condition, right? Because it still remains to check the boundary conditions to confirm all the field there. Okay, and if we look at this problem again, as I mentioned before, this problem is traction problem, right? So we don't specify any displacement at point on the boundary. So we know only the traction condition at every point on the boundary. So to check the boundary condition, we just simply use stress that we got before, right? Because the displacement is not known on the boundary. Now to check the boundary condition, we start by checking on the surface S1, S2, and so on. Okay, so we expect that all 6 surfaces, the condition can be satisfied. Okay, and we also expect that besides the satisfaction of the condition on the boundary, we also expect to get all constant as well. Okay, let's start by looking at the surface S1. On the surface S1, we know that the outward unit normal vector pointing in the opposite direction to the x1 axis. So n is simply -1, 0, 0, right? So if you look at the way to get the attraction due to the stress field that we got before, we take stress that we got from the previous step, multiply by outward unit normal vector. For this particular case on the surface S1 is simply -1, 0, and 0, right? And then you multiply stress that we got before with the normal vector like this, and then we end up with the traction here. So this traction is simply the traction generated by stress. So this is what I call sigma multiplied by n, or T that generated by stress field. Okay? But this one is the one that prescribed. Sorry. Okay? This is the one that prescribed. Because on that particular surface, we know the normal pressure here, right? The pressure P0 pointing in x1 direction. So and we don't have shear traction. So the traction is prescribed simply P0, 0, and 0. Okay. Based on this condition, what can we conclude? What can we conclude? So the component here have to be 0. The component here, the first component here, the whole thing here that we got here. Yeah, the whole thing here should be P0, right? And the whole thing here should be 0. This component as well. So this end up with 3 conditions here. Is that clear to you? So the first condition we just simply obtain from the first component condition, right? So that one have to be equal to P0. But this one, I just simply divide the whole thing by mu, and I just get the relationship between B12 and B21, because B12 plus B21 have to be 0. So B12 is simply the negative of B21. The same thing for B13 and B31. They have to satisfy this condition. Okay, so this is the condition on the constant B. Some entry of the constant B have to satisfy this to make sure that, okay, the condition on the surface S1 is satisfied. Okay, I can do exactly in the same way for the surface S2 here. Okay, so I generate the traction by stress. I just simply change the normal vector from -1, 0, 0. I change that to 1, 0, 0, because on this particular surface, the outward unit normal vector point in the same direction as x1. So this is the n that we got for this surface. Okay. So you just simply multiply sigma by n, and you end up with this. Okay. Again, the traction generated by stress have to be the same as the one that prescribed. So we have the prescribed pressure here in the negative x1 direction. So don't forget the negative side here. So this end up with what? 3 conditions as well, like this. Okay. So you can see that the condition that I got here, we get the condition exactly the same as the surface S1, right? So the reason that I didn't put the number of all this condition, because the first condition that I got from this surface is exactly the same as the first equation there. Or I can say that if the constant B satisfied the first equation here, that equation will be satisfied too. The same thing for the second and the third equations, right? Because B12 equal to minus B21 here, we get exactly the same condition. So I can say that if the constant that we have here satisfy the traction on the surface S1, it will satisfy the traction on the surface S2 as well. Okay. Or I can say that I cannot get any new condition on the constant from the surface S2. Okay. There is a question from you guys. I don't understand your question. Can you explain here? Can you explain me about your question that you? Can you explain me here? Can you use the microphone? Explain me about your, because I am not sure that I understand your question. Okay, so then I will skip your question here because I can talk to you later because I don't understand, because the problem that I focus on here is not what you mentioned in the question, right? Because here we deal with this particular problem. As I told you, if you deal with different kind of problem, so you need to look at the condition that you have to satisfy for that particular problem. Okay, so if you have to deal with different type of boundary conditions, you have to focus on the problem that you solve. Okay, you cannot just simply do exactly the same as what I did here in details. The overall step should be the same. So if you have a displacement boundary condition, you have to verify that as well. If you go back to look at the condition that we have to satisfy, it depends on the problem. So if on the boundary you have both displacement and stress, displacement and traction prescribed in different part of the boundary, so you have to check both of them. Okay, but in this problem, we have only traction condition prescribed on the boundary. So that is the way that I try to verify here. So if you need to check the displacement, you have to check that. Okay, but it's problem dependent. Okay. Let me move on here. So the boundary condition on the surface S1 and S2 are verified here, or I shouldn't say verify. I try to satisfy the two conditions, and I end up with the condition for getting the constant B. Okay, I have three conditions for the two surfaces. Okay, now I can move to the surface S3, 4, and 5, and so on. And let's see what will we get. Now, if we look at the surface S3, that surface, we follow exactly in the same way, but now we change n, right? Because the outward unit normal vector for this particular surface is simply 0, -1, and 0, because the normal vector pointing in that direction. Okay, and we get the traction generated by the straight field. Okay, we just simply perform the multiplication here, so we end up with this traction, and that have to be exactly the same as traction that prescribed here. If we want to satisfy the boundary condition on the surface S3, what should we get? We should get something like this. Again, you can see that the condition 2, that B1, 2, and B2, 1 have to be opposite inside, like this. This is not the new condition. We also got that condition from the previous two surfaces, right? The thing that we got here that is different from the previous case is this condition and that condition. So I named that equation 4 and 5 respectively. Okay. Now I look at the surface S4. Okay, I change the outward unit normal vector to 0, 1, 0, because on that surface, the outward unit normal vector pointing in x2 direction. So you can see that we end up with the condition similar to the previous one, except that, okay, we have the negative side here, but the negative side here can move to the right-hand side. Now, the condition here and that condition are identical, right? So we get the same condition here. but they are not new. Okay, that one is similar. That one is identical to 4. Okay, and this condition and that condition are identical to the previous one that we got from the surface S1, and that one are identical. Okay, so I can say that when we enforce the boundary condition on the surface S3 and S4, we get 2 more conditions. Okay, now we have 2 remaining condition, that 2 remaining surfaces that we have to check. Okay, now if we look at the boundary condition on the surface S5, okay, we get something like this, because on the surface S5, the outward unit normal vector pointing downward like this, right? So n is simply 0, 0, minus 1, right? And then when you multiply stress by that normal vector, you end up with this. Okay. Again, you set this equal to the prescribed condition on the surface S5. On the surface S5 is traction free. What do I mean by traction free? The traction is prescribed, but it's 0. Okay, so we know the traction here equal to 0. So then we enforce that term equal to 0, and we end up with this condition, right? And the first 2 conditions here are exactly the same as what we got before. So these 2 conditions are not new. Okay, the only one that is new is the last one here. So I named that equation 6. Okay, and if we do exactly the same way to the top surface S6 here, so you will see that, okay, this equation and that equation are exactly the same, except the minus sign here, and that is, it doesn't matter, right? Because on term on the right hand side is 0, so you move this to the right hand side, will be exactly the same as this one. So what I can conclude that the 3 conditions I got from the surface S6 are not new. Okay, so you can see here that, okay, when I enforce the condition on 6 surfaces, or I enforce the boundary conditions at any point on the boundary, I end up with 6 conditions on 6 conditions on the constant B, right? Okay. If you take a look, we have equation 1 involve B11, B22, and B33, right? That equation 1 involve B11, B22, B33. And equation 4 involve B11, B22, and B33, right? And equation 6 involve B11, B22, and B33. So based on this 3 equations, we should be able to solve for B11, B22, and B33, form a system of 3 equations, right? Okay. Here you can see that we have equation 1, equation 4, equation 6. All of them here contain 3 unknown constants, right? So we can solve the system here simultaneously.
Ajahn?
Yes?
I think in equation 6, you miss, it must be ever 0, 0.
Okay.
Yes.
That is right. Okay. So this one have to be 0. Okay. That is a mistake. Okay. So equation 6, term on the right hand side is 0 because we don't have the traction apply in the x3 direction. Okay. Thank you very much for pointing out that error. Okay. So we have all 3 equations here. So now we can solve them simultaneously. Now you can get the constant B11, B22, and B33. I replace mu and lambda back into the equation because the data that we are given, is the Poisson ratio and Young modulus. So I plug this thing in, or you can plug it in later. You solve these three equations first, and then plug in this mu and lambda, and you finally get B11, B22, and B33 like this. Okay, solve this linear equation. You know how to solve it, right? Okay, you learned that from Ajahn Chapan, right? So solving linear equation is very simple. Okay, we have only three equations, so you can solve them, and finally you get B11, B22, and B33 like this. How about the other three equations that we have before? Equation 2, 3, and 5. We cannot solve them to get the value of the constants. For example, B12 and B21. The two there are related by a single equation, right? Equation 2. And B13 and B31. B23 and B32. We face with the same situation, right? We cannot solve them because we have only one equation that related to the two constants. The only thing that we can say here, we can say that B12 and B21 are not independent. They are related to each other like this. So now if I set B12 equal to B3, so B21 gonna be minus B3, right? So I call the constant B12 and B13 and B23 as B3, B2, B1 respectively. Okay, so now I can say that the three equation 2, 3, and 5 can reduce from, can reduce the number of constant from 6 into 3. Okay, before we have B12 and B21, B13 and B31, B23 and B32. Now we can reduce to B1, B2, B3 based on the relationship here. Okay, so three equations here just simply allow you to express all 6 constants here in terms of only 3. Okay. Now what we have here is like this. This is the displacement that we got, right? We start from the linear form of the displacement field. One week satisfy all the boundary condition. We finally get U1, U2, U3 like this, right? Now we're done with confirming the displacement field that we guessed. Why I can conclude in this way? Because we already check all the conditions that we need, right? We check the governing equation inside, and you saw that okay, the gas displacement field here generates strain and stress that satisfy all governing equations. And the form here can also satisfy the boundary condition at all surfaces if the constant take this particular form. Even though we cannot get B1, B2, B3, and also A1, A2, A3 that we assume at the beginning cannot be determined here, that is fine. Because if you take a look at the problem that we focused on here, the problem, we didn't restrain the body against the movement, right? So the rigid body motion is still there. So if you look at the term, the last term here, the last group here, if you investigate all those terms carefully, you will see that all of them there just simply represent rigid body motion. A1, A2, and A3 represent rigid translation. And B1, B2, B3 here represent rigid rotation, right? So now we're done. Even though we cannot determine all the constant here. And we can conclude that, okay, the displacement that we guessed is a solution of the problem, okay? And it's not unique because the constant that related to the rigid body motion cannot be determined uniquely for this particular problem. Okay, is that clear to you? If the body that we look at here have some part of the boundary that we know the displacement, now you have to check the condition on that size by looking at the displacement you got here and try to get the constant. Okay, but here we don't need to do that because there is no displacement boundary condition. If you want to get the remaining field, like strain and stress, it should be simple now, right? Because we already know the displacement field. If you want to get strain field, you can just simply plug in, right? Right? Go back to the first step after you get the displacement field. You already generate strain field, right? And it's stress field, right? Here, you can see that you already generate strain and stress before. Once you know the sum of the constant, you plug it in here. You know that term disappear, right? Right? So some of the term disappear, that term disappeared, that one, two. So all this disappear. So B11, B22, and B33, you obtain already from solving the three equation. Okay, and the same here, that term disappear, the shear component disappear, and you get only the term along the diagonal, and you plug in the constant that you got before. So finally you get strain and stress field. Okay, like this. And now we're done. Okay. Now you can compare the method 1 and method 2 here. Which one you prefer? You may like the first approach. Some of your friend may like the second one, the second approach. Okay. So I will not say that the first one or the second one are simpler. So it's simply the matter of preference, right? Because you may like, you may have more intuition to guess the stress field, and some of you here may like to guessing displacement field. Okay, but I try to show you the two different guessing strategies, and once you guess the different field quantities, we have different way to check or to confirm that the field that we guess is a solution of the problem. What happens if we cannot satisfy the condition, some condition or all conditions? Now you have to realize that the one that you gave there may not be the good choice. You have to go back and correct the guess form and verify it again and again until you get the final one. Okay, you may not be able to get the final one if the problem is more complicated than this. Guessing the right form of the solution is not easy at all. Okay, so I will have one problem in the quiz next week that asks you to to get the solution of the problem like this by using the guessing strategy. Okay, so if I feel like that the problem is complicated to you, I may give you the form of the solution, or I may guess the form for you. Or if I think that okay, the solution of the problem is simple enough, the data that I gave you, the geometry, material properties, or loading condition are simple enough, I may not give you I may not give you the right form. Maybe you have to guess by yourself. Okay, so So you will see one problem related to the lecture that I covered today. Okay. I will stop this lecture here. Do you have any question about anything related to lecture 3?
อาจารย์ครับผมมีคำถามครับผม
ครับ
คือว่าอย่างในตัวอย่างข้อนี้เนี่ยมันไม่มีตัว rigid friction rate ใช่ไหมครับแต่ว่าใน assignment เนี่ยมันมีตัว rigid friction rate อะครับผมเลยสงสัยว่ามี rigid friction rate กับไม่มี rigid friction rate อะในการคิดอะครับมันจะมีอะไรที่มันแตกต่างไปจากเดิมไหมครับหรือว่ามันก็ไม่เกี่ยวกัน
ก็ผมตอบไปแล้วไม่ใช่เหรอเมื่อกี้นี้
ผม
ก็
ไม่
ผมบอก
ค่อย
แล้วว่า
เก็ต
ผมบอกแล้วว่าเวลาคุณเช็ค condition ก็ต้องดูว่า condition นั้นมันมีอะไรบ้างใช่ไหมผมตอบไปแล้วนี่ก็คือมันก็ขึ้นกับปัญหาที่คุณจะต้องพิจารณาสิก็ถ้าคุณบอก condition ที่ surface ยกตัวอย่างอย่าง surface 1 surface 2 surface 3นะในที่นี้เรารู้ traction เราก็เช็ค traction ถ้าคุณรู้ displacement ก็ต้องเช็ค displacement ดิใช่ปะมันก็ตรงไปตรงมาเนาะผมไม่มั่นใจว่ามันมีประเด็นไหนที่ทำให้คุณสับสนหรือเปล่าก็ผมไม่ได้บอกนะว่าทุกหน้าจะต้องเช็ค traction อย่างเดียวก็เรารู้อะไรเราก็เช็คกันนั้นสิใช่ปะอย่างในกรณีนี้เนี่ย S1 S2 S3 S4 เรารู้ traction เราก็เช็ค traction ถ้าเกิดในการบ้านคุณรู้ displacement ก็เช็ค displacement ใช่ปะคุณก็ต้องฟอร์สให้ condition นั้นมันสอดคล้องอ่ะมันถึงจะเป็นคำตอบได้ไงแล้วคุณก็ไม่ต้องกังวลถ้าเกิดคุณใช้เมธอด2ในที่เนี้ยคุณมี displacement คุณมี strain คุณมี stress ไปแล้วตั้งแต่ต้นอยู่แล้วอะถ้าเกิดสมมติว่าคุณบอกว่าคุณอยากจะเช็ค displacement condition บน surface คุณก็เอา displacement มาเช็คดิแทนที่จะเอา stress มาเช็คใช่ปะนะก็ขึ้นอยู่กับปัญหานะผมย้ำเลยนะว่ามันขึ้นอยู่กับปัญหาที่คุณจะหาคำตอบมัน problem dependent เนี่ยหมายถึงว่าเราจะเช็คในรายละเอียดทุกขั้นตอนเหมือนกันเป๊ะๆทุกปัญหาเป็นไปไม่ได้เพราะฉะนั้นรายละเอียดปลีกย่อยในแต่ละปัญหามันก็อาจจะแตกต่างกันแต่ขั้นตอนโดยรวมก็คือทำเหมือนที่ผมโชว์ในนี้เลยอ่ะเนาะใช่ไหมเพราะว่าผมจะไปทำให้คุณดูทุกตัวอย่างมันคงเป็นไปไม่ได้ใช่ไหมแต่หลักการเนี่ยมันเหมือนกัน
ขอบคุณครับ
โอเคป่ะไม่รู้ว่าชัดเจนป่ะ
ชัดเจนครับขอบคุณมากครับ
โอเคครับโอเค your friend just asked me the something that related to your homework assignment because in your homework assignment on part of the battery the displacement right because you try to restrain the movement of the body in the normal direction by the frictionless rigid block right so in that case on the surface is the condition that you have to verify are different from what I have here because if you compare the condition that for example if you look at the surface S1 for this particular problem the traction there the traction in all three directions right T1 T2 sorry T3 right but let's say that okay I replace this surface by frictionless rigid block now that okay the traction is not prescribed in the x1 direction anymore right so if you replace this by the frictionless rigid block so now on that surface now that U1 is 0 but T2 and T3 are still prescribed equal to 0 so instead of having T1 T2 T3 equal to 0 now you have U1 equal to 0 and T2 equal to 0 and T3 equal to 0 okay so now the condition that you have to verify on that surface will be different okay so when you try to verify the conditions on the surface or on the boundary of the body please be specific to the problem that you focus on okay is that clear to you guys okay be specific to the problem that you you deal with. Okay.
I have a question, Ajahn.
Yep.
The solution according methods too. We have this displacement field EU1, U2, U3 with B2, A1, B2, B3, and according to the uniqueness of solution, I think it have a contrast rate.
Why?
As
I didn't say if you go back, I think you confused about the uniqueness of the solution.
Yeah.
Because I when I conclude about the uniqueness, I conclude about the uniqueness for strain and stress. Strain and stress are always unique. It doesn't depend on how you restrain the body against the rigid body movement. But the displacement field, I didn't say that the displacement field is unique all the time.
Yes.
The displacement field is unique if and only if the body is is restrained against the rigid body motion completely. If that is the case, the displacement will be unique. If you go back to the proof, I show that in the proof, right? I didn't say that the displacement is unique all the time, right? Okay.
Yeah.
In the case that the body is free to move rigidly, I say that okay, the displacement is unique up to the part that produce the non-zero strain. You can always have the rigid body motion there. So in this case, I think that the thing that you got here is right, because the body that you look at here, we didn't constrain any part of the battery to prevent the rigid body movement. So the rigid body motion have to be there, right? So this term cannot be determined that is right, because if you say that the displacement is unique, you can see from the problem that you focus on here, right? That the displacement can be vary without changing the stress inside. You just simply hold the body here and walk around, and you can see that you always add the rigid body movement to the body, but it doesn't change the stress and strain field. I'm not sure that I answer your question or not.
That's my problem. Just my answer. Just my question.
Okay. So I can tell you that, okay, if we go back to take a look at the uniqueness, just a second. Okay. I think I showed that in the proof somewhere. Just a second. Here, right? If you take a look at the end of the proof, we have strain epsilon bar, right? Epsilon bar ij equal to 0. But that one cannot imply that U bar have to be 0. So U bar here have to be expressed in terms of the displacement that is rigid body motion. Okay, so that part, that's what I call rigid body motion. So now, if you take a look at the definition of U bar is simply U1 minus U2, right? Right?
Yes.
Maybe you have to remove the bar here. So we shouldn't have the bar here, right? So this is wrong. So we shouldn't have the bar here. Remove the bar here. So U1 and U2, the difference is the rigid body motion. So what does it mean? It means that the displacement that we have for the same body can be non-unique, but the difference between the two solutions is simply the rigid body motion. So there are two cases that possible. If the body that you look at here, you prevent the rigid body movement completely. So term on the right hand side here will disappear, right? Because if you don't have rigid body motion, that rigid body motion have to be 0. So that term disappear. AI and BJ just simply known, or you can say that they are zero. So now you can say that U1 and U2 have to be the same. But if the body can experience rigid body motion, so AI and BJ there are arbitrary. So now you can see that U1 and U2 are different, right? Okay, is that clear to you? So I didn't say that the displacement field is always unique. Okay, the part that is unique is the part that generates the strain. Okay, the part that generates zero strain may not be unique, depending on how you restrain the body against the rigid body motion. Okay, is that clear?
Yes. But in particular case, in a particular solution, it mean there are many solutions for UI. I mean, in a problem, we have many UI.
That's right. That's right. Because in your case, you can think about that. Okay, if you hold the body and move around without changing the traction you apply, you can see that you can see that strain and strain may not change, right? But the displacement change when you move, because I'm not sure that it's clear to you or not, but you can think about holding the body here. Okay, let's look at the body. This body. Let's say that you hold the body here and apply the pressure equal to P0, and then you move around. Okay, you hold the body in your hand and apply the force like this. Let's say that you walk around. You hold the body and you walk around without changing the value of the force that you apply. What happened to the body? Strain and strain will be the same as you know, if you stay still, okay, you hold the body, apply the force, you can get strain and stress.
Yeah.
Okay, and then you move around without changing the force that you apply. I think the strain and stress inside will not change, right?
Yes.
But the body experience rigid body motion there, because you hold the body and you move around. So now you introduce the rigid body motion to the body. Is that right? So now you can see that you can always add rigid body motion part into the displacement field without changing strain and stress. So that aspect we can say that the displacement is not unique for this case.
Yeah, I see. It mean I when I move, strain and stress can not change, but the position of each point
change. That's right. That's right. Because the change of the position, that is the displacement field, right?
I see.
Yeah, because the displacement is simply the change of the position. Because the change of the position without the change in strain, we call the rigid body motion.
Yes, maybe change the position, move.
Yeah, because that is the definition of the displacement field, right? So so the displacement U1, U2, U3 here, this is the measure of the change of the position at any point in the body. Okay? And if you make the change of the position in terms of the rigid body motion, that part, it will not produce a strain. Or you can try, if you are not sure, plug in only this part into strain displacement relationship. You will get zero strain. Or the change of the position of the material point in the body that are given in this form will not produce any strain. Okay?
Yeah.
So what I can conclude for this problem, A1, A2, A3, B1, B2, B3 can be arbitrary. Okay? It doesn't matter. The value of AI and B IR. This is the field that satisfy all the conditions that we have. Okay, so even though we have AI and BI involved in the displacement field, but strain and stress field doesn't involve this constant anymore, right?
Yeah.
So all the field that we have there satisfy everything. If you look at the the procedure that I did here from the beginning, you can see that all conditions are satisfied. Okay.
Yeah. It mean it depend on the initial condition.
Boundary condition, not initial condition.
No, not initial condition.
Yeah, the initial condition, you talk about the dynamics problem, but if you talk about the boundary condition here, so it depends on the boundary condition, right? So if you constrain the body properly against the displacement in all directions, so the term in that I group here disappear, right? Or known. They will be disappear or they will be known. If, for example, if you let's say that okay, you put the support here.
Yeah.
So now if you put the support there, you can see that A2 may be 0, right?
Yeah.
Because you cannot have the rigid translation in that direction. Is that clear?
Yes.
Yeah. Or if it's not 0, it have to be constant that you can obtain by by setting the condition on that side. It can be 0 or known, but it cannot be arbitrary if you put the constraint like this. Okay.
Yeah.
So what I can conclude here, the constant that involved here can be obtained or determined completely if you provide the restraint against the movement of the body. Okay.
Yeah.
Anything else? Any question? มีคำถามอะไรเพิ่มเติมไหมครับ